Hi guys, this video is on creating iterator objects and then using them to do practical things in code. The previous videos have gone through kind of the theory of iterators and all the terminology involved. Now we're going to see how you actually use them to do useful things. So this video is going to go over how to create iterators with the begin and end functions. There's both the forward and the reverse version of that for bidirectional iterators. How to use these top-level functions, these ordinary functions, next, prev, advance, and distance. There are convenience functions that help you work with iterators. How to loop using iterators. The most common use case, I think, for iterators is to loop through a container. There's two ways of doing that, a conventional for loop and the range-based for loop, which is new for C++11 and is more convenient in most cases. There's the const iterator issue. We'll get into that and show you how to insert and erase elements using iterators. Finally, the range constructor I will introduce. That's a way of initializing a data structure to contain elements that come from iterators. I want this to be a short video, so I'm not going to give you every single detail on these operations. For that, go to reference documentation such as the c++.com link that I showed there. The idea of this video is to just show you what you can do with iterators and where to find more documentation. If you want things like examples of code, read those documents. So first, how to create an iterator object in the first place so you can start working with it. That's with the begin and end functions. So on any container that supports forward iterators, including the three we're covering, singly linked list, doubly linked list, and vector, there's a container member function called begin. So if container is a container object, you just do the .begin member function call, and that returns a vector that's at the beginning location. So if vect is a vector object, then vect.begin gives you a vector that's at the beginning location of that vector. And likewise, container.end gives you a iterator that's at the past the end location. Some data types support reverse iterators. Of the ones we're covering, forward list or singly linked list does not, but doubly linked list and vector do. And the way to get a reverse direction iterator is rbegin. The same begin word, but r in front of it, r for reverse. And similarly, the reverse end iterator is rend, or rend, maybe you could say. Okay, so there are these four convenience functions that help make code a little more convenient or readable when working with iterators. First off, there's already a way to mutate iter to the next location. Mutate is a technical term that means change. You know, like a mutant has been changed. So if I mutate object iter, then I'm changing the iter object to become something different than it was. I'm not leaving it alone, I'm changing it. So there's already a way to mutate an iterator to go to the next location. That's iter++. There's an alternative, which is this function called next. And what next does is it is a function of two arguments. It takes an iterator object and a number of steps you wish to take, and it returns iter incremented k times. This is not mutable. So it does not mutate iter. It leaves iter unchanged. It creates a new iterator at this new location. It basically does plus plus to iter k times. It leaves the iter alone, though, and returns you a new iterator that's at that location. Note that there's a default argument of k equals 1, so you can call next with only one argument, and it will move only one location over. There's an analogous function called prev that just moves in the previous direction. It decrements, in a sense. And there's a mutating version of these functions called advance. What advance does is you give it an iterator and a distance, which could be positive or negative, and it increments k times if k is positive, or decrements k times if k is negative. Advance only works in the negative direction if iter is a bidirectional iterator, as you would expect. And it returns void, because what advance does is it mutates the iter, it changes it. Finally, there's a convenience function to calculate the distance between two iterators. So if I have a range starting at start, ending at end, the distance function returns the integer count of how many locations are in between them. And we're using the same convention that a range starts at start and goes up to, but not including end. So if start and end are at the same location, the distance is 0. They're the same location. If end is 5 steps ahead of start, then this function returns 5. Part of the point of these is to give us the functionality of raw pointers. This is something you can do on a raw pointer. You can subtract one pointer from another to get their distance apart from each other. And when we switched from raw pointers to iterators, we didn't want to lose that power. So this distance function lets us do that in a encapsulated abstract way. Now let's see how to loop through containers using iterators. Here's an example where I just created a vector of floats. This creates 10 copies of the number 2. It's just an example. And I've written this two ways, one with plus plus to advance to the next location and another with the advance function to move to the next location. So here's how it works. I need to declare an iterator. And the data type for an iterator within a vector of floats is vector float : iterator. So that gives me the iterator data type. And then I need an identifier for this. I'm going to call it IT. My personal habit is to use IT for an iterator. I usually use I for an index, and just to make it kind of clearer in the code that we're not talking about an int index, I make it a different name, IT. But some people use I. It's not a big deal. I initialize IT to be at the vector's begin. We loop as long as the iterator is not at the vector's end. And every step of the loop, we do IT++ to move to the next location. Observe that this really resembles a for loop that uses pointers to go through an array, and in spirit it still resembles your usual I equals 0, I is less than n, I++ kind of loop. What I do at every iteration is I dereference IT. The dereference operator follows the iterator to the location it's at and returns the element at that location. So IT is a location within a vector, star IT is the float at that location. And for clarity, I'm initializing float x to hold that location. You wouldn't really necessarily have to do this. I could just see out star IT. That would work as well. But in order to segue into the range-based for next, I wanted to give this a variable name. And on the bottom of the slide here, I've got the same exact loop. The only change I've made is that instead of doing IT++ to move to the next location, I'm doing advance IT by 1. And, that's maybe a style thing. Personally, I think that's more readable. IT++ might be perhaps confusing, but advance iterator by 1, I think, is more clear what the programmer's intention is there. Now let's see the alternative of the range-based for. This was new syntax added in the C++ 11 version, so it's on the newer side. And the goal of this is to cut down on some of the clutter and busy work of writing these loops. There's all these good reasons to use iterators instead of indices or pointers. They're encapsulated, they're abstract, the compiler gives you better error messages, stuff like that. But one downside is there's kind of a lot to type out here, and it can get tedious to write all this stuff. And this is a really common thing to do, loop through every element of a container. We'd like that to be more concise and not so much busy work. So the range-based for gives that to us. Here's the general pattern, and I've got a concrete example on the bottom. The general pattern is you say for, open parentheses, and then right here we have a declaration for a variable that will hold one element of the container at a time. It's like my float x back here. Float x represents the current element. So you need the data type of one element, the identifier or variable name that will be one element, a colon, which is kind of means like in or from, and an expression for a container. And then you have the body of the loop, and inside the body of the loop, you can use this variable. The variable represents the current element we're on. In order for this to work, container has to be a data type that has valid begin and end functions that return iterator values. So here's a concrete example. I've got my vector of 10 2.1s, and then I say for float x, that's going to be my variable that holds one element at a time. Vect is the container that is a data structure with begin and end functions, and then in the body of the loop I can use x. X represents the current element. So what happens is this basically is the same thing as these here. The compiler kind of expands this out for us, but we don't have to see it or type it. It just says, the way I would read this is, for each x in vector, do this stuff, print out x. So that is a lot more concise, and in the common use case of needing to loop through every element in a container, this works great. Okay, let's get into the const iterator issue. First, we have to explain what a non-const iterator is. So the plain iterator we've been using all along, like std vector iterator, is a mutable iterator. Again, a mutable thing is a thing that allows mutation. It can be changed. So a ordinary iterator or mutable iterator is one that allows the individual elements to be changed. So it's legal to do something like this. I've got a for loop that starts an iterator at a vector's beginning and goes until the end the normal way. And for each element, I do star it equals 0. This is changing the current element to become 0. So this loop has the effect of changing all elements of a vector to become zeros. It mutates that vector vect. And sometimes that's a fine thing to do, but it's a compile error if vect is const. Some variables can be declared const, and a const variable is a constant. It's unchanging. You're not allowed to ever change it. So in that case, if vect was a const vector, we would have a contradiction here where the vector is never to be changed, but here I am in the loop changing it. So this code here would trigger a compile error for that reason, just to kind of illustrate how this works. Let's say I have this print function. It takes a constant vector reference v. So v is a vector that should never be changed. So far, so good. I've got this loop that kind of looks okay. I say vector float iterator it starts at the beginning as long as we're not at the end plus plus. Float x is the current value and print it out. So in fact, I'm never changing the contents of the vector. However, this will get a compile error right here at the it equals v.begin. And the reason is v is a const vector. So v.begin gives a const iterator, an iterator that does not allow changing. And then here I go trying to put this const iterator that doesn't allow change into a regular iterator that does allow change. So the compiler is recognizing this looks like I'm kind of trying to break the rules here and gain mutation access to an object that should never be mutated. And there's a compile error that's triggered. It's not a very readable one, but it basically is saying that's a const container. You're not allowed to mutate it. Don't put it in a mutable iterator. So there's this other data type of a const iterator. A const iterator is an iterator that works all the way we've been covering, but it does not allow elements to be mutated, and so it's compatible with const containers. The data type is the same thing except the word const underscore is put before the iterator. So there's standard vector iterator is an ordinary mutable iterator, and then standard vector const iterator is a const iterator that allows you to loop through a vector but never change the elements. The functions to get the begin and end are the same names, but with the letter C for const. So C begin, C end. The reverse ones are a little weird. Constant reverse begin, constant reverse end. So CR begin, CR end. So here's how I could fix that compile error, make my print function work. I've got print, it still takes a const vector of floats, and now I'm declaring a const iterator it. Instead of regular iterator, it's const iterator. And instead of begin and end, I call C begin and C end. And that would make the compile error go away because now there is no way that it can ever possibly change the elements of v, so that's compatible with the const declaration. The range-based for automatically determines which one to use. So range-based for back here has some logic in it that if this variable is const, then use const iterators. If it's not const, then use mutable iterators. You don't have to worry about figuring that out. Let's see how to use iterators in some other ways. One is to insert elements into a container. So insert is a member function in vector and list and other containers. Here's how it works. There's a few ways of calling it. You can call insert iter value, and that inserts the given value at the given location iter, and that takes constant time. You can insert n copies of value at a given location, and that takes linear time. And you can insert a range of elements. This is where that range thing comes in. So at location iter, I want to insert all the elements starting at start, ending at end. Start and end usually come from a different data structure, and that takes linear time in the number of elements that are actually getting inserted. You can also erase individual elements. This is, again, a member function on vector and list. So vector.erase or list.erase given an iterator. You can, when you call it with one argument that's an iterator, that removes just that one element. And it's linear time on a vector because of the scooting or shuffling that needs to happen, but it's constant time on a doubly linked list. That's one advantage of a doubly linked list. You can delete one element at a known location in constant time. You can erase a range of locations starting at start, ending at end, and that takes linear time on both doubly linked lists and vectors. The last thing we're going to show you here is the range constructor. This is kind of like insert a range. It creates a container and also inserts elements in a range defined by iterators all in one step. It's available for all the container types, forward, list, vector, and so on. So you call the constructor, which would be the data type name. You give it a start iterator and an end iterator. And what that does is initialize the container. So it creates it, initializes it. And to begin with, it has all of the elements starting at start and ending at end with the usual convention that we include start but don't include end. This is linear time. And so this is kind of a shortcut. If you know you're going to create a data structure and then put elements into it, you can do it all in one step by calling the constructor with these iterators. And it might also be a little bit more efficient than creating an empty structure and then adding elements over and over again. For example, the vector, if you do it that way, where you create an empty vector and add elements one at a time, it does a bunch of resizing. But instead, if you say create a vector that has this elements to begin with, it can compute the right size of the array and allocate it just once and then fill it in. So for example, here's how you could use that. Let's say I've got vector A that holds these numbers, and then I want to make a linked list of ints that has everything A has. One way of doing that is I could say construct B, and then I'm calling a constructor with 2 arguments here, and pull from A's beginning and end at A's end. And this would make a copy of the elements in a linked list data structure all in one line of code. It's pretty convenient.